Okay, so welcome everybody. This is part of the Earth and Environmental Sciences and Physical Geography seminar series, our spring seminar series. And I'll start off with a little bit of advertising. So this obviously Daniel Schindler is speaking today, but we have been having seminars about once a week, and if you're interested in being added to our spam list, I'd be happy to arrange that you are spammed once a week or whenever we have a talk or some other special event going on. So just talk to me afterwards about that. So Daniel speaks this week. Next week at the same time, one of our PhD students, Mesvin, is going to be talking about long-term and spatial distribution of greenhouse gas fluxes in apple orchards and vineyards in the Okanagan Valley. So that's his PhD thesis. The following week, actually, and this will be on a Monday rather than a Thursday, Al Woodbury is going to be talking about direct use geothermal energy overview and status. And then at the very end of May, Andrew Weaver is going to be in town, and we've arranged for him to give a presentation when he's here. We tried to get him during the semester, but he's tied up in the legislature, you know, now being a member of the provincial legislature. In any case, at the end of May, he'll be talking about global warming and the British Columbia Clean Energy Challenge. So that's the bit of advertising. Now I should introduce today's speaker, who is Dr. Daniel Schindler, and I understand that he actually is a UBC alumnus. He went to University of British Columbia on the Vancouver campus years ago, back in the 1980s. And following that, subsequently, he went on to University of Wisconsin, where he did his master's and PhD. And when he did his master's and PhD there, he was very shortly thereafter hired by the University of Washington, where he now holds the Harriet Bullitt Endowed Chair of Conservation in the School of Aquatic and Fisheries Sciences and Department of Biology at the University of Washington. And so anyway, welcome.
Does anyone know about laser pointer?
Yeah.
Yeah. Thanks for the invitation to come to a seminar out here. I'm not sure this is the title I actually submitted to Ian, but anyhow, this is the title I'll roll with today. And I'm going to really, there's two words here that I want, or two phrases I'm going to pick on a little bit. And these are phrases that are really quite heavily used in sciences, thinking about what are we going to do about ongoing climate change. Okay? One is prediction. Okay, this is something that, of course, all sciences hold as their holy grail, and in a lot of cases, the value of science is often valued based on how good our predictions are. Okay, that's something we hold dear to our hearts as scientists. As we move forward with global change, this is something we hear a lot about by environmental scientists, that to manage for ongoing global change, we need to develop better predictions. Okay, so I'm going to challenge that. The other thing I'm going to talk a little bit about is this precautionary principle, which again in environmental sciences people are talking about a lot. And the way this is typically interpreted is that if we do some assessment of some resource and estimate how quickly it turns over and these sort of things, we can come up with what we may consider a sustainable rate of exploitation of that resource. And the way people usually implement the precautionary principle or interpret it is, well, if X is what we think is sustainable, maybe we should just back off a little bit and go a little more conservative on the side of X. And I'm going to offer an alternative perspective on what the precautionary principle that I think is probably a more worthwhile interpretation of it. And you'll have to stick with me for the next few minutes while we get to that point. So I'll hold you a bit in suspense. So clearly, I'm guessing with this crowd, you can probably at least browse through this. You probably don't need to. The reality of global change is obviously real. It's now getting into politicians' heads. The public is becoming increasingly aware of it. Big corporations are developing strategies to deal with the fact that Earth is warming, humans are the major cause of it, and the other reality is that we often forget about it. It doesn't matter what we do now to change our impacts on the climate system. there's enough momentum in this climate system. We're going to be living with a warmer future, at least for a century, probably longer. There's questions about how much warmer it's going to be, but the reality is the world is going to continue to warm. And the last 3 decades, this is from the latest IPCC report, we're on this steady marchward up in terms of global averages. There's some discussion about a stall in the rate of increase, but the reality is, I think just about any scientist with half a head on their shoulders is saying, look, the world is going to be warmer in the future, and what we're talking about now is how to reduce how warm it's going to get and how long this is ultimately going to last. So in terms of ecosystems, I'm an ecologist. I would call myself an ecologist. Ecologists, it's probably never been a more important time to be an ecologist in terms of having relevance to society, because part of the issue is these changes in climate are going to impact the ecosystems that we depend on. Okay? Our water, our wildlife, our agriculture, our fisheries will be affected by ongoing climate change and future climate change. Okay? So the question is, what are we doing as scientists to prepare society, prepare policymakers, etc., for what's going to happen to the systems that we depend upon? And I would argue that the overriding perspective is really about this, which is that our focus should really be on improving our forecasts of how systems respond to climate, okay? And then we manage around those forecasts, okay? And this is over a decade old at this point, but they're just talking about it's critically important that ecologists develop better forecasts, okay? Here's a more recent one, and this is, I think, reflects the typical paper, the typical grant proposal that you read in ecological literature, which is that, and the key here is accurate predictions of responses to ecological responses. Climate change is crucial for conserving and protecting natural and human influenced ecosystems. Okay, so there again, the assumption is the predictions are what we have to manage around. And then they go on to say, and these cannot be complete without a deep understanding. Okay, in this case, they're talking about the recognition of species interactions. So the argument here is, to prepare for this warmer future, we need to develop really good predictions, and we're going to manage around these predictions, and that the way to achieve better predictions is by deeper, richer understanding. Okay? Here's another one. This is a recent paper. This is taking a poke at fishery science by a bunch of ecologists who are saying, look, fishery science has been a disaster in lots of places, and the reason for this is because fishery scientists don't understand the complexity of ecosystems. Okay? So my pitch right now is that ecosystems, whether they're heavily human influenced or as pristine as we like to think they are in some places of the world, they are so complex that we will always have really limited capacity to understand them and to make forecasts about them. And this is not necessarily the type of sentence that makes a good first sentence in a paper you submit to Science or Nature or your next grant proposal to answer. But I think we need to realize if we're going to be effective, we have to step back and realize our forecasts, our understanding is always going to be limited. And as a result, we have to start thinking about other ways to deal with this. So here's some examples that talk about, these are, that demonstrate the complexity of ecosystems. Okay, this is from the Gulf of Alaska that has been the subject of a bunch of long-term scientific surveys in terms of what the dominant species in the ecosystem are that are subject to commercial fisheries. And these are just 3 standardized net tows from the same area. In the 70s, you can see that trawl came up. It was basically all crustaceans. It was crabs and shrimp. By this transition period between 77 and 80, we started to see a mixture of pollock, halibut, and prawns, or shrimp and crabs. And this is what that same trawl survey looked like a few years after that. The crustaceans are essentially gone. It's all pollock and halibut. Okay? Fishing may have caused some of this. This co-occurred with a time period where there was a big change in the Pacific Decadal Oscillation, which drives the climate of the North Pacific. And the point is, this system went from something that appeared very stable in the 50s, 60s, and 70s to this switch simply being flipped essentially overnight, and now we have a different system altogether that's been relatively stable now for a few decades. Here's some paleo data from the off Santa Barbara, I don't know what it's called, Anyhow, it's this anoxic basin right off of Santa Barbara that it's one of these rare marine sites that has anoxic sediments, and fish scales accumulate there. And this set of really, this is a blurry figure, but these are just showing the scale deposition rates of Pacific sardines and northern anchovies. And I think this is a 2,000-year time frame here. But here, the same ecosystem, all presumably experiencing the same general oceanographic conditions, the same climate regimes, show two things. First of all, the two species are both very erratic. They have big highs and big lows, and the big highs and big lows are not necessarily synchronized. But we're also seeing changes in abundance from decade to decade that are showing at least two orders of magnitude differences in abundance. Okay? This is before humans are doing much to exploit this system. This is before human-induced climate change. This is what we should consider as natural variability in the system. Okay, can we understand these systems? You know, my argument today is we have really limited capacity to do so. And one of the reasons is because ecosystems have these problems associated with the scales in space and in time that organize them. So this is one of those diagrams that you give to your grad students to read and they promptly glaze right over, but I think they're one of the most important types of figures that we should think about when we try to understand how ecosystems are organized. So this is what's called a Stommel diagram, and these are just scales of space in logarithmic scale. So from -6, these are kilometers, -10 to the -6 to 10 to the 6th or so, and then time scales from seconds to tens of thousands of years. And if you go to any ecosystem in any place, what you see at any snapshot in time is the interaction of all these processes that are occurring across timescales that range from seconds to tens of thousands of years or longer, and from spatial scales that operate on the course of, say, meters in the case of food choices, or I think that says beaver or something right there. This is a boreal system that has beavers and beavers and moose, and I don't know what else is on there. The point is simply that your typical ecosystem, one of the reasons we have really limited capacity to understand them is because they're organized by processes that are arranged across huge dimensions of space and time scales. And then the complication is that as humans, we just get tiny little peeks at this diagram. We can go and sample, a long-term study in ecology, maybe 10 or 15, 20 years, and that's just one little tiny slice through this. In the case of paleo studies can of course go for thousands or longer periods of time, but they're usually in individual places or a couple places. So we only get peeks at this, and as a result, we have really limited ability to understand this. Now, people often say ecology is not rocket science. And my response to that is, yeah, it's way harder than rocket science. Because when you're building a rocket, you know what the thing's going to look like when you get it all together. The ecosystem, you don't really know what it looks like because you're just getting little peeks at it from time and space. And a really important paper that described this is one by Cy Levin. It was his MacArthur Award lecture a couple decades ago. It's cited really highly. I think it's cited often for the wrong reasons. I mean, people cite this because they have the point that any observation you make of a natural ecosystem, the answer you get out of those sets of observations depend on what space and time scales you aggregate across, which is true. But the other thing he talks about, which is ultimately important, is that the dynamics of systems depend on processes that play out across these space and time scales. So when we talk about making forecasts into the future about how our ecosystems are going to respond to climate change, we need to be able to understand those processes. We need to understand how those processes play out across space and time scales. And this is where I get quickly pessimistic and say, you know what? We're never really going to understand how these things are going to play out. We have to be a little more humble about the power of our science to make good predictions for the future, and therefore our ability to manage prescriptively. It's often the case that people say, oh, we'd love to make a prescriptive management decision to move into the future. And as soon as someone says we want to make a prescriptive management decision, I walk out of the room because I don't think you can. Okay? It's going to be trial and error, and it's going to always be operating around limited certainty. Another interesting paper that starts to get at some of these issues is a really bizarre paper by Ram Myers. where he did an interesting study. This was in '98, and he dug out about 47 published studies where fishery scientists had looked at recruitment dynamics of a commercially important fish species. And basically they asked, were there climate signals in the recruitment variability? 47 papers published that demonstrated or could show statistically significant correlations between recruitment from year to year and some climate index like sea surface temperature or wind intensity or effluent intensity. What Myers did is return to these same data sets 10 years later and reanalyze them and ask, well, how many of these held up? And here's the answer. 1 out of 47. Okay? So two things are going on here. One, there was probably publication bias. You have a bunch of data sets, and we all tend to do this. You bounce around in these data sets until you find a significant correlation, and where you go publishing it, trying to infer mechanism from it. And of course, as you get more data, it's often the case that if it was a random relationship to start with, it only is expressed as random after you get enough data. The other issue that's going on, of course, is that the world is probably not stationary. Again, a lot of ecology is based on the assumption that if you want to understand, for instance, the effect of one predator on another prey, that you can describe that relationship by some function with a set number or set values of the parameters, and once you know it, that relationship is going to hold through time. That's what we would consider stationarity. Or similarly, if the average temperature out here is some given value, it will produce X amount of water out of the streams the following summer. The assumption of stationarity is that the function that is defined in one time period translates into some other time period. And it's quickly become apparent in lots of environmental sciences that stationarity is a really dangerous assumption, that the relationships between different variables is always changing through time. So if you read this paper a couple years ago, they argued you got to use fancier models and fancier statistics and account for the fact that the strength of relationships is changing through time, and that's what we should be using when we manage water resources. Again, I sort of believe that, but they're continuing, they're perpetuating this idea that we can understand the systems and management has to be focused on rich understanding that produces good forecasts. Maybe for water we can do that. When we get to biological components of ecosystems is where I have some doubt. Okay, so let's talk about salmon. Most of my work is on the salmon of Western Alaska, and the group that I'm part of has been working in Western Alaska since the late 1940s, when the cannery industry came to the University of Washington, because Alaska was not yet a state, and they said, look, we need some scientists on the ground. We're concerned that we're over-harvesting the fish because they've declined the last 15 or so years. We want people to do some science and tell us what are the reasonable ways to exploit these fish. Okay, this was in the 40s, and the cannery people, people making millions off this resource, were the ones who actually started thinking about what we now call an ecosystem-based perspective on the systems that they were actually exploiting and making a buttload of money off of. They wanted scientists to go in, look at the lakes and the rivers, look at the fishing itself, and figure out what is the sustainable way to exploit these systems. So in the process now, my generation is sitting on 60, 70 years of data, in some cases more, where we can look back and ask, how has climate affected salmon in Alaska? And to get to this perspective of the scaling, this hierarchical scaling of ecosystems, the work I'm going to show you is occurring with this going on in the backdrop. This is the biomass of salmon in the North Pacific Ocean since 1925 to a few years ago. And this is something that I'm guessing everyone in the room doesn't, or very few people in the room have appreciated. There's way more salmon in the North Pacific now than there was in the 60s, 50s, and 60s. It's like 3 times more biomass of fish in the ocean. Okay? A lot of it is hatchery production from Asia. Japan and Russia are pumping a lot of hatchery fish, mostly chum salmon and pink salmon. Alaska pumping out a lot of pink salmon as well. But this slice here, this is North American sockeye. You can't really see it on this but production of sockeye has pretty well doubled in the last 50 years. Okay. Again, you don't hear about this from the perspective of the media. You certainly don't hear about it from the perspective of B.C., because what dominates B.C. media and salmon is the fact that Fraser River's tanked recently. But the reality is, this, we now understand pretty well, was a response to climate warming, and this Pacific Cable Oscillation shifted the system to a more productive state, and it's filled up with salmon. So anything we see at a local scale is occurring with this going on in the background. In another part of the ecosystem that there's those fish are swimming around competing with. Okay, so let's go to Bristol Bay. This is Alaska out here. This is the Alaska Peninsula swooping out to the left. And this area here is Bristol Bay. It was heavily glaciated. The glaciers disappeared, probably 15,000 years ago, so it's been free of glaciers for a while. But the reason this is such a productive site for salmon are all these huge lakes. There's Lake Ilion that's almost 2,000 square kilometers. Each of these other lakes is as big as Lake Okanagan Lake and bigger. This is an area, this is from 2 IPCC reports ago. This just shows you the rate of warming globally, and of course red areas are areas that have warmed fastest in the last century. And you can see that Western Alaska has warmed as fast as any other part of the world. And this is the time frame over which we've collected data on salmon. And now we can ask, well, at least given the climate change we've seen in the past, which has been about 1 degree Celsius change in the last 50 years, which is a pretty big number when we think about what the projections are moving forward, we can ask, well, how did salmon respond to climate change in this last century? So we do that with a bunch of different ways. I'll start with the just the commercial catches of salmon, and these are obviously not the total abundance of fish. The reality is these fish are harvested really heavily. They're harvested at about 60 to 80% exploitation rate. So this is most of the fish. Okay. So this is when the canneries first developed in Bristol Bay. They wiped out the Columbia River stocks. They moved north to Alaska and set up shop. They caught all these fish out of sailboats. And you can see within about 15 years, they ramped up to almost full capacity. So catch in 1903 was 15 million fish per year. And you can see for 120 years, there's year-to-year variability, of course, but in fact, the catches have increased since the mid-70s. They've decreased a little bit the last 5 years, but basically you have a system that has produced enough salmon to keep a commercially viable industry in the game for 120 years. And we could call this resilient. There's been a lot of climate change here, and people have stayed in the game here, even though they've pounded the crap out of these fish. They're capturing 70% of them before they spawn. So how can that be? Well, part of the answer here is if you look at the colors here, each of these is the major fishing districts. The fish are harvested in somewhat terminal fisheries where they're caught as they come back to the river mouth. And what you can see is, for instance, this blue, which is the Naknek Kwijak, that's the Iliamna system, really dominated catches for most of the century until the last 20 years or so. And their proportional contribution has declined, particularly in the 90s. But what was interesting is it was compensated by increased production by some of the neighboring rivers. Okay? And we know from genetic studies, from archive samples, that it wasn't that the fish swam back to the wrong river and were caught in the wrong river. It's just that the populations that produced the fish in one river declined during a time period when the other rivers that are within 100, 200 kilometers away started booming. Okay, so there was some compensation there. So that same theme is expressed at a whole bunch of scales that we have data for, from everywhere from the North Pacific Ocean, which is the fact that it's increased over the last century. Those fish swim back, they separate into 9 major rivers, and then within each river, we now know that there's dozens to hundreds of individually adapted populations. These fish come back, and the fish that spawn in little streams and warm streams are different than the fish that spawn in cold streams or warm streams, etc. So there's a lot of local adaptation, and what we have here is a hierarchical structure to the overall system, both in terms of the habitat that's expressed at fine scales, but also the genetic structure of the system is expressed at fine scales, sort of mesoscales, and then the aggregate scale. This is where the fisheries operate. They're integrating sort of among these sites to all of Western Alaska. Okay, so to get an appreciation of where climate is done here, let's look at the returns to each of these rivers, in this case for the last 60 years or so when we have the best quality data. And I'll just play out the returns here. I've relativized them so that 1 is the long-term average, there's 10% of the long-term average, and there's 10 times the long-term average. And these are the data in terms of returns. So this is catch plus what's escaped to the rivers through time for one river. And this is a logarithmic scale. So this stock is going from anywhere from 5 times the long-term average to 2 or 3% of the long-term average, depending on what year you draw here. So remember, this is a sustainable fishery. If this was your salary, if this was your monthly income or your annual income from the university, and one year the university says, we're going to give you 3% of your salary, and then unpredictably 2 years later they say, well, guess what? This is your lucky year. You get 5 times your salary. You know, are you going to stick around and stay in the game playing that one? Hell no, you're going to be out of there. So how can this be sustainable? You know, a lot of the people who fish this, they live there, and there's no alternatives for employment. Yeah, maybe the government gives you a little opportunity here and there, but fishing is what keeps these communities rolling. How is it sustainable? Well, this is how it's sustainable. This is where I've overlaid all of the other rivers in the system. Again, if you squint your eyes, you see some general increases, for instance, in the mid-70s. But what the fishery is seeing is the average across all of those stocks. And that's what I'm showing you in the dark black. That's what the fishery sees from year to year. Okay? Because when one river is crashing, by chance, an adjacent river may be booming. And the fishermen can move around. There's some penalties to moving around. But the management system has kept the the management system has allowed fishermen to maintain the option to move around and pick off the hot spots and avoid places where the resources tank in any one given time. So we started using this term portfolio effects to describe this. This is much like the same strategy you would use if you diversify your investment strategy. You know, if you're thinking seriously about your retirement, you don't go buy the hottest stock of the day and hope that it's going to pan out in 30 years from now. You know, despite having perfect data on the markets, financial analysts still don't understand it. And one of their most common strategies is spread your risk across the diversity in the stock market. In the case of the fisheries of Bristol Bay, they're not doing this explicitly, but the reason they're sustainable is because the landscapes are producing these portfolio effects to them, and therefore they're sustainable. So we can see this in a bunch of ways. Here's the returns to Bristol Bay. There are the returns to each of the major rivers. There's 1, so there's the long-term average. And the complexity keeps getting more as you dig deeper into the whatever the right word is here, deeper into the watershed. So here's returns to individual populations on a river system. So now we're going from a little more than 1% to almost 8 times the long-term average from year to year. Each line is a different population. And then within each stream system, there are different life history strategies of the fish. A female salmon will drop her eggs in the gravel. Those eggs will spend about a year in the gravel. They swim out to the lakes. Then they spend either 1 or 2 years in the lake. Then they go to the ocean. And then they spend 1, 2, or 3 years in the ocean before they swim back to spawn in fresh water. Now, in an evolutionary sense, what that female has done is spread the risk of some environmental catastrophe to her juveniles. Okay? So if we just look at the dynamics of the dominant cohorts in each one of those streams, the variability keeps blowing up. Okay? So now we're going from less than 1% of the long-term average to over 10 times the long-term average in the individual components of this system. But they don't all occur synchronously, and because they're asynchronous, you get stability in the overall system. These are the scales where ecologists tend to work. Okay? We may go to our favorite stream, or if we're really crazy, we work on 2 or 3 streams, and we hope to develop deep understanding of that stream. And the hope is that we can apply it back to the broader spatial scales where humans are actually exploiting and interacting with the system. Look at this. I mean, I think we got to take a second look at this and realize, I don't know if we're ever going to really understand what's going on here. But if we keep this complexity here, we may have a hope in maintaining some reliability of the overall system. Okay, so why is this? Is this just sampling error, or is there something real going on? And there's the genetics. I mean, the genetics of these different populations is clearly different, and there's got to be some filtering of the climate, for instance, by the fish themselves. It's easier to appreciate the fact that the habitat is also filtering climate. Okay, so if you're a fish living in a stream, you don't experience climate directly. You experience climate as it's filtered through the local landscape and expressed in the conditions in the freshwater habitat. So I'll give you a couple examples of that here. These are all catastrophic die-offs of populations within the Wood River system where I spend most of my time doing research. Each one of these, if it was in the lower 48, would be on an endangered species list. You know, there would be not billions, probably millions of dollars poured into trying to help these poor fish out. But this is all from a watershed. This is Mother Nature in action. Okay, all should be considered natural phenomena. So here's a stream called Berm Creek. It flows out of the mountains up here into a big lake. You can see the edge here. And in fall, if the water level's high, the big storms will build up this big berm of gravel here. Okay, that's there in the early spring, or throughout the winter, early spring. When the snow melts in early spring, you get enough energy in that stream, it blows out the berm. The fish come back in midsummer, and they swim happily into their spawning grounds and do their thing. But this was a year, the summer following a winter drought. Okay, no energy in the stream that spring. Gravel didn't get blown out, and fish came back to spawn, and they all died. This is about 5,000 sockeye salmon dying with their eggs in them. Okay, the bears and the birds were really happy, but there was no successful reproduction that year. Okay, and it was because of a winter drought. Here's a river maybe 7 kilometers away, and in this part of Alaska it's pretty dry during the summer. By late August, early September, it rains a lot and water levels come up. And here's a little river that has maybe 10 to 15,000 spawners, and they spawn in late August, early September. That was my sabbatical year, so I was up there till October, and this is what the spawning gravels look like in October. What you're looking at here, that's a moonscape for all the salmon nests that went dry that year because there was a fall drought. The rains never showed up in September. Here's a different population on a lake, one down in the river system. Here they wiggle into this little stream here. It's about 3 meters wide and 3 kilometers long. And that little stream, it's this deep, produces on average somewhere between 50,000 and 100,000 sockeye salmon per year. Okay? Unbelievably productive. But the challenge to these fish is they have to swim out of the lake and over this beach here. It's a very low gradient beach, forms this delta to get into the stream. And on a low summer water year, when there's a summer drought, you get this big delta here, and these fish literally have to crawl their way up over the gravels to get into the stream proper. Well, there are these big furry brown things running around here, picking these things off, and 60 to 70% of them can die at the delta before they get into the spawning habitat. And that system is dependent on summer droughts. Okay? So the same watershed, one population is susceptible to winter droughts, another to fall droughts, another to summer droughts, and all of these things don't necessarily happen in the same year. You got beaver dams doing their thing all the way across the landscape. There's a whole bunch of other things going on too that we don't necessarily see. The point is not everything is synchronized. Regional weather is being filtered through local habitat scales. So in 2009, Lauren Rogers did a nice analysis where we used our 60 years of data at the individual stream level and fit a standard, what we call a stock recruit function for the fish, which is what fishery scientists tend to use to estimate sustainable harvest rates. That just relates how many fish are produced by a spawning population on the x-axis. So the number of spawning stock versus the number of recruits that are produced. Okay, and then in those models we included a bunch of environmental covariates that would affect salmon survival. And what we're showing here in each dot is the coefficient for each of these variables for each population. And you can see, for instance, this one is ice breakup date in the spring. In general, all of the coefficients are negative, which means if there's an earlier ice breakup, there's a higher survival of fish from that cohort. Okay? And here is sea surface temperature in their second year, so that's when they hit the ocean as smolts. Again, they tend to mostly be positive, but look at the scatter around each variable. Okay? Again, it appears that different populations respond differently to the same general climate signal. We don't necessarily know why. The statistics simply tell us that these things have different responses to the same regional climate signal. So is it possible, the common argument here is that what I'm talking about so far is really the year-to-year buzz in the data, and that if we talk about sustainability, we talk about long-term climate change, we really need to be thinking about longer time scales, okay? So that if you want to think forward 50 years, you have to think about what's the moving average for this system and what is it going to look like 50 years from now. So the question then would be, does diversity play out over longer time scales? And in this case, we use some of the tricks of Limnology, which this group I think is pretty well acquainted with. And this is simply taking a simple gravity core out of lakes that are nursery habitats for these sockeye salmon. The sockeye come back from the ocean with an enriched isotope signature. Fish die after they're spawning. All those nutrients get washed into the lake, and they're deposited in the lake sediments, basically in proportion to the salmon abundance. So you take a little core like this and get, say, 500 years of data, the history of that lake, and just ask, well, how enriched is the isotope signature through time? And you can use that to infer a relative abundance of fish. So we pulled together all the data sets for Western Alaska. A group of us got together, and it was a very difficult process. But anyhow, we've kind of got a publication out of it. Anyhow, this landscape here produces about 60 to 70% of the world's sockeye salmon. So we're not talking about an insignificant part of the global habitat for sockeye salmon. And we just asked, well, how coherent, how synchronized are the stocks when we look at this from century to century in Western Alaska? And this is really the take-home message here. In green, so what we have is the year 1500 to the present, and this is the N15 in the sediments. The green sites are ones that have waterfalls on them. They shouldn't have had fish in them in the last 500 years. All of the blue ones have sockeye in them now. And two things to note here. The salmon systems are firstly more enriched, but they're also far more variable. Okay, there's more variation in the N15 in the sediments in the salmon systems than compared to these reference sites. But the thing I want you to notice here is pick pairs of lakes from anywhere in this matrix and pick pairs of lakes that show the same wobbles. Turns out we have really good dates on these things, so it's not just a dating problem in the sediments. And yeah, okay, so here's Packers Creek, which is in Cook Inlet, and there's Carlick Lake. These are two of Bruce Finney's sites. These seem to be strongly correlated with each other. But they're not correlated with any of these other things. So you can pick pairs of lakes that have some coherence, but there's very little coherence across the landscape. You can do this a little more elegantly by doing a principal components analysis on those traces and ask, are there common signals that are shared amongst all those lakes? And here are the common trends that are shared amongst the lakes. The first four principal components shown here. The only one that's statistically significant is the blue one. That's the first principal component. It grabs about 40% of the variance across the system. The other ones are not significant at all, at P 0.05 or 0.1 or something. But of course, what we see here is the one dominant signal that's shared among those sites is really driven by this decline in the last 100 years. And people have recurrently misinterpreted this. They say, well, there's fewer salmon here now than there were in 1900. Of course, that's not what's going on. It's that the salmon were intercepted, shipped to Japan, and those isotopes are sitting in a sewage lagoon in Japan right now. Okay, or they're back into the atmosphere. So the fish just were intercepted, their isotopes weren't deposited in sediments, and that's what drives the coherence across the landscape. At longer time scales, there's very limited coherence through time for 500 years over a time period where we know there has been lots of climate change. So again, you get diversity across the landscape in response to some regional climate signal. So are these just esoteric concerns and arguments, or do they affect anything about people who live here, whether they're subsistence fishermen or commercial fishermen? And we have a grant right now to try to figure out what's the socioeconomic value of this complexity in the landscape. But we're going to come up with more elegant answers, I'm sure, but I just want to show you a simple simulation that I think captures the fact that reliability in the system matters. And that is to think about how the system is currently managed from the commercial and fishery standpoint. So right now it's managed around what's called an escapement goal, which is that the fishery scientists have the number of fish that spawned in any given year, and they know how many fish returned from that cohort, okay? And from that, they can estimate the optimal escapement to produce maximum sustainable yield, okay? So for Bristol Bay, the escapement that produces MSY is about 10 million fish. Okay, that's what fish should be put on the spawning grounds. The fisheries officers then allocate any return above that value to the fishery. Okay, so if 30 million fish come back in a year, the fishery gets to harvest 20 million of them, 10 million go back to the watersheds. If 8 million fish come back in any given year, there's no fishery. And they just say, sorry guys, go home. So they have total power to do this on a day-by-day basis. Okay? So now let's play out what it would look like over 100 years if you just had random chances from one year to the next based on the variability we see in Bristol Bay. And what you see is that from year to year, of course, there's lots of variability. But in 100 years, 4 years fail to meet the escapement goal, in which case there would be 4 years where there would be no fishing allowed. Okay? So now let's go to a future Bristol Bay where we've eroded the diversity in the system. Okay? But we still maintain the same long-term average catch shown here in the green line, same as that as 32 million fish. And this is what we've done in the lower 48. We've basically trashed the habitat, we've pretended the habitat doesn't matter, and we've made up the difference with hatcheries. Okay? And hatcheries basically produce stupid fish. They all go out into the ocean in the same time. They use the same habitat. And you can continue to ramp up hatchery output and get your returns. So you could envision Bristol Bay where the same average return was there, but now you increase the variability to the level we think would be here if you stripped out the diversity. And now ask how often the fishery's closed. And now you're seeing that 40% of the time, you're not going to get any fisheries. Same long-term average yield, but variability is increased to the point where now you're getting runs of 3 and 4 years in a row. And those are probably the conditions that make fishing communities go bankrupt and people move to the big city and go on welfare. So we think reliability is a big part of maintaining resilience in these small communities in this case. What about all the wildlife? You guys probably know that there's lots of wildlife that depend on salmon. Whether they're sport fishermen, some of them can be considered wildlife, but there's bears, there's birds, there's a whole bunch of different species that rely on this big source of salmon nutrients that come back from the ocean every year. And the question is, do they also value or benefit from the diversity in salmon? And I'll show you one example of this in one life history trait of salmon, and this is the timing that the fish spawn. Okay, so this is all within the Wood River system. Each line here is an individual population, and the blue line is the period that they're actively spawning at any given site. So your typical population fish are spawning for about 3 weeks. Okay, across the watershed though, fish are spawning beginning in mid-July and continuing through to early to middle October. The reason this is important is that the consumers, whether they're things like rainbow trout or scavenging gulls or brown bears, can only access these resources when the fish are spawning and in shallow water. So if everything spawned at exactly the same time, the bears, for instance, would have basically 3 weeks to fatten up on salmon. The fact that there's diversity across the landscape means there's opportunity for these bears to move around from site to site and have access for almost 3 months. So just to show you how this plays out, this is the Wood River system. Each dot here is the average seasonal summer temperature, and you can see there's this mosaic of stream temperatures, and this correlates into timing of when the salmon spawn. So some of these streams are 2 or 3 degrees all summer long, some are 14, 15 degrees. Salmon spawn later in the warmer sites, and then they spawn earlier in the cold sites. I don't really have time to go into it. I'm happy to talk about it, but it looks like it's a function of the watershed features. The west side of this watershed is very mountainous, and a lot of snow is captured at higher elevation. And based on isotopes of hydrogen and oxygen, we estimate that these streams over here are mostly driven by snowmelt over the course of the summer, whereas the streams on the flatter side of the watersheds are mostly rainwater. And this correlates. Here's some watershed features. Here's how much rain is in the stream flow, and the colors here are the stream temps. So rain-dominated sites in flatter watersheds are where fish spawn late. That same watershed has steep catchments that have lots of snow in them, and they tend to be colder. So again, you've got diversity in the landscape. So the question is, do consumers shift this, we call it a wave of resources played out across the landscape. And I'll give you a couple examples here. This is for rainbow trout. This is a little stream that has a cold tributary, a warm tributary that comes out of a small lake, and it mixes down here. These are the sockeye salmon coming in to spawn, and basically the fish move out of this big lake and they spawn in the cold tributary first. This is basically late July. By late August, all the fish are spawning. This is actually a genetically distinct population spawning down here in the main stem. And these are the rainbow trout. This doesn't show it too well, but in a nutshell, the rainbow trout first feed on salmon eggs here. That's where all the rainbows are. By September, all the rainbows are down here gorging on eggs. All of these predators, whether they're bears or rainbows, on any given day, if they're in there with the salmon, they are bloated with food. So food resource amount is not what limits them. What limits them is the length of time they have to digest and process that bear material. How about bears? A lot of brown bears up here in June and early July, well in this case late July. This is a sow scratching on a tree. She's probably about 8 feet tall. Late and tall, 3 little cubs here. She is a bone rack. She probably weighs, I don't know, 350 pounds, but when you see her walking, her ribs are all sticking out, her femurs are sticking out. Bone rack. And this is what she looks like 6 weeks later. Let's say a picture's worth 1,000 words, video's worth millions, but anyhow, here she is scratching. She is so happy and fat, and the cubs are grown up, and you know, she can double her mass in one season because there's lots of salmon, but there's also the contraction season that's driven by the geomorphic complexity that allows the resource to be available for a longer period of time. And these are just we just put cameras out on tributaries and ask where are the bears. Okay? And these are the number of pictures on a cold stream, so the color here matches the temperature. No bears seen on that stream until the 15th of July when the fish show up. We get a whole bunch of, these are cumulative distributions. We capture a whole bunch of bears on cameras, and then they leave about the 15th of August. And let's overlay a bunch of other streams in the system. Bears were on all the cold streams early, and then by the end of the season, they're all on all the warm streams. So they can surf this wave of salmon across the landscape. Gulls scavenging, doing the same thing. So here's a term that I think we need to use more often, which is when we think about wildlife and the ecosystem, we need to think about what are the options. What are the options for the fish? What are the options for the wildlife? And it's often the case as we develop landscapes, we take options away from wildlife. And if we want to talk about resilience to climate change, one of the things that's going to give ecosystems resilience is by maintaining options for the system. Okay? Give you one more example of that. This is occurring at a much finer spatial scale. This is work of a guy named Johnny Armstrong, who is also a grad student of mine. But again, you get these big differences in temperature regimes. What looks like dust here, these are all sockeye salmon queuing up to go up and spawn into this stream here. And what's interesting about this stream is there's a lot of off-channel habitat. There's beaver meadows at the top, and there's a lot of this thermal heterogeneity. And it's full of coho salmon. And the coho, most of their energy, most of their growth is supported by feeding on sockeye salmon. Okay, some is juvenile, so that poor little sockeye is about to get nailed by that coho, but mostly by feeding on eggs from spawning sockeye salmon. So the coho, I don't know what else does that, but the coho, this is a 2-year-old coho, and it's going to fatten up feeding on the eggs of sockeye salmon. Okay, so what Johnny recognized is that the stream actually gets colder as it moves downstream. So up at the top of the headwaters, you get these big beaver meadow complexes where the water may be 12 degrees Celsius or so. And as it drops down through fairly low gradient systems, the bottom kilometer or so is much colder. And that's where the sockeye salmon spawn, in this cold, well-oxygenated water. If you go out and ask where are the coho salmon, they're all up here, sitting in warm water. And the question is, why are they sitting in the warm water if all their high-quality food is down here? Well, Johnny started opening up some of these fish and realized, well, these guys are full of sockeye eggs. And this is, 1 to 2 kilometers downstream in this little tributary, and these are coho salmon that are, the size of your finger or smaller. So what he hypothesizes what's going on here is that they have heterogeneity in the system in terms of the temperature that they actively exploit. And the idea is that the cold water supports sockeye salmon, but the coho, if they fill up on a belly full of grease, which is what these eggs are, they literally can't digest the stuff if they sit around in cold water. And as a result, he thought, all right, they're going to swim upstream for 2 kilometers and digest in the warm water. And he told me this, these fish are this big, and it's like, yeah, right, go smoke another bowl. So what he did was put in these pit tag readers and put little pit tags in these fish, caught some up here, and then asked how much do you see them moving back and forth. Okay, so here they are. This is not a random sample, this is our best sample. But here's a fish that was tagged, so this is section 3, this is section 1. Tagged in section 3, and about 3 days after he tagged it, it swam downstream over the antenna at section 2, down to antenna at section 1, spent a couple hours there, turned around, swam back high. Spent 3 days, did it again. Spent 4 days, did it again. Repeated it all summer. And what we think's going on is they have this, like you eating 15 Big Macs, you're probably not going to eat for a while. Okay? And in the case of these salmon, they're going back with this belly full of incredibly high quality stuff, but to turn that into growth, they have to digest it, metabolize it, and they're constrained in cold water. They move into warm water and they do it. And these are fish that are this big, and they're making these migrations over the course of several kilometers. So what they're doing is actively exploiting the heterogeneity in the watershed. He kept working on this. These are his first 2 years. Okay, what I'm showing you is the water temp in the lower stream and the upper stream. We have this nice contrast. He did it again. The contrast was even bigger. The fish grew a little faster. And he figured, all right, I got a nature paper. I'm just going to do it one more summer. And this is what happened this next summer. Is we got a lot of rainfall. These dots are the rainfall on all the days. And during 2009, it just started pouring. And there was enough water ripping through that system that it just washed out this thermal heterogeneity. And he figured, all right, well, there goes my nature paper. What's going on? To his credit, he kept looking at what the fish were doing. The expectation was once you lost the temperature variation that they would start growing slower. So we got a wet year in 2009, we got a wet year in 2010, and we got another dry year in 2011. And this is what it all boils down to. Hopefully everyone drank some coffee, but here's a weird figure that I think tells us what's going on. Here are the stream temperatures for 2 kilometers of stream. This is the outflow of the stream, that's cool because there's groundwater. Here's the top of the stream, 2 kilometers upstream. Colors are the temperatures. So in the 2 dry years, warm at the top, you get through this transition, cold in the fall wake going downstream. Here's another dry year, warm in the fall wake, cold in the fall wake at the bottom. 2 wet years, all the stream temperature. Here's the dry year again. The question is, where are the fish? Now, each of these little, whatever you want to call those, the little branches here are off-channel habitats. And the dot tells you how many juvenile coho are found in each one of those segments. And then the color is the temperature they're in. So in the dry years, you see, first of all, most of the bubbles are at the top of the stream. Okay? And the colors, except for that one and that one, are all orange or red. Fish are sitting in warm water. Okay? But everyone, or most of those fish are in the fall wake habitat. So the question is, what happens in the wet years? First thing to note is the distribution shifts downstream. Okay? But notice all of the bubbles are still orange or yellow. Okay? Even though the fall wake is now blue, it's the same temperature top to bottom. In this case, stream flooded up, spilled out of its banks, created off-channel habitat that now warms up. And the fish go from migrating longitudinally to migrating latitudinally or laterally on the order of meters. So they're actively finding and exploiting the temperature variation, and the habitat looks different depending on what the flow conditions are. And it turns out there are no differences in growth rates of juvenile coho across these 5 years, even though the environmental conditions are vastly different. Complexity in the landscapes providing options for these guys, and they're exploiting those options. So when we evaluate what's fish critical habitat, we got to be really careful that we don't go in and spend 2 or 3 years assessing what the critical habitat is for a watershed or for a stream. We have to recognize that our assessment of critical habitat depends, intimately on what the prevailing weather conditions are in those years. And again, we've got to play our risks a little broader and think about, let's maintain the complexity across the watershed. And when we think about what are the risks to ongoing climate change, what can we really do about it? Well, part of my argument here is maintaining diversity in landscapes is one way to spread the risk to ongoing climate change. Let's keep options open for things we care about. In the case of salmon systems, a lot of the options are created by disturbances, in this case hydrologic disturbances. This is a stream that used to flow over there. We came back one spring and took a shortcut through a forest, and this is what salmon habitat looks like. These are the processes that generate different types of habitat that are valuable to fish at different times of the year, different seasons, etc. If this was Washington State, the Department of Transportation would be out there with their bulldozers trying to put the damn stream back in this channel. Okay? That's not what we should be doing with these habitat. Let it play out. Let the disturbances beat it up a little bit and generate the habitat. And we all know of Aldo Leopold, and he's the hero of conservation. And one of his most cited comments is this: "To keep every cog and wheel is the first precaution of intelligent tinkering," which is true. But I would extend it to let's maintain and keep the processes that generate the cogs and wheels in the first place. And disturbance is part of this, whether it's forest fires, whether it's flooding. This is what generates heterogeneity in the landscapes. I'm going long here, so I'm going to skip over this. And the point is simply that I think what we need to be doing is thinking about, come back to this precautionary idea. I think the right way to approach precautionary is to first be honest about our abilities to make really high quality predictions. Where I would argue we're never going to have good quality predictions about things like fisheries or wildlife population dynamics. So what we need to do is develop strategies that are robust to those uncertainties. And when it comes time for implementing the precautionary principle, what we should be doing is maintaining flexibility. Not necessarily about backing off on our harvest rates or using less at any one time. It's more about being ready to change course if suddenly what we're doing is the wrong thing. If we're using too much water in that river because suddenly we're in a dry spell, we better have some mechanisms for doing something different. In the case of Bristol Bay fisheries, they have flexibility because they're managing across the landscape, and they have the regulatory authority to shut a fishery down in 1 day's notice, and there's no debate about it. People will whine about it, of course, but there's no debate. They just do it. But they have options for the fishermen to go elsewhere, and in this case, this is the Alaska Department of Fish and Game. What they're doing is developing genetic tools so that they can intercept fish coming back from the Gulf of Alaska back here in a test fishery, run the genetics on the fish that are being caught, and use that as a tool to protect weak stocks that are coming back to the main fishing districts. So it's a techno fix in a lot of ways, but it allows them to monitor the dynamics that are coming back. So for instance, here's a fishing district where there's 3 major rivers that swim through this fishing district. There's a period of time where one of them was actively depressed, and they had to back way off and fish in all of them. Now they have the genetic techniques where they can assess how many fish are coming in, and if it's an emergency situation, they'll back off. But if it's not an emergency, they'll allow them to keep fishing. So what should we do about it? I mean, it's pretty clear our landscapes are going to look different in a warmer future. Can we predict what they're going to look like? Some things I think, I think the hydrology we can probably do better than some things. The geochemistry probably can do, better than the ecology. When we get to the ecology, I don't know, there's not much we can do. But does this mean that we're handicapped? I would say no. There's lots we can do now. Let's maintain the diversity. Let's maintain the properly functioning watershed, and that builds us a way to spread risk. And to cite one of my favorite lines from a movie is, some people hear this talk and they go, God, this guy is anti-science. And it's heretical to say that science has limited capacity to predict the future. And, all right, some people are not going to like that message. But I think it's a reality, and I think if we're serious about making a difference in conservation and resources, we got to start figuring out ways to spread our risk a little bit. And this precautionary principle is about keeping options open for the ecosystems, but it's also about keeping options open for our management organizations. Don't get locked into one way of doing things and never be able to get out of it because you become entrenched in bureaucracy. And then from a purely ecological standpoint, stability and productivity derived from diverse and changing habitat. This is a theme that's been around in ecology for decades. But when you start applying it to watersheds, and in this case the salmon ecosystems, it really does hold a lot of water. And with that, I'll happy to take any questions. Before I walk off that. Yeah.
Do you think, in your diversity model, do you think that fish hatcheries have any role to play?
So I often trash on hatcheries like this guy over here dropping eggs in. I mean, the reality is that there has been a lot of hatchery reform, and there are certainly hatcheries where the habitat is so far gone that the hatchery does play a role in maintaining that strain while we go through the process of rehabilitating that habitat. So I think hatcheries are part of the solution, but in a lot of cases, like in Bristol Bay right now, the watersheds are still intact, and there's serious proposals to come up, and we can put a hydro dam on that river. We'll just put a hatchery in, and that'll compensate for habitat loss. Or Pebble Mine, I don't know how many people have followed Pebble Mine. It was going to be the largest sulfur-rich copper and gold mine in the world, or in North America, right in the headwaters of these systems. It was going to leak, sulfates all over the place, and people were worried about the pit and destroying habitat in the local area. But what I argued to them is, look, you got to think about the broader landscape, where all the roads and culverts are going to do. And their response was always, how don't you just put hatcheries in? No, support the system. So in a system like that, I would say, look, hatcheries are a last resort when you are really against the ropes, and then maybe they can help. But to pretend that hatcheries can compensate for lost habitat is a pipe dream, I think.
Does that apply also to B.C.?
Yeah. I mean, Mother Nature is always going to do better than a hatchery will over the long term. I mean, yeah, there'll be some piece of stream, for instance, that is just not very productive for some variety of natural reasons, and maybe then you can do better out of a hatchery. But if you start opening up to big spatial scales, hatcheries, I think our tendency is to rely and believe too much on hatcheries for producing sustainability.
What's the effect of salmon farming on the health of the wild salmon?
In Alaska?
Oh, generally speaking.
That's a good question. So in B.C., I think it's an overblown problem. I really do. So I was at a workshop, maybe last year, I guess, at SFU, where they pulled together a bunch of people to talk about how to implement the Cohen Commission recommendations for the Fraser River. And, the whole workshop got hijacked by a couple people whose firm belief was that salmon farms were what was causing the decline in wild fish. And I was like, well, hang on, you guys. Don't put all your eggs in one basket about salmon farms, because, first of all, the evidence is pretty weak for things like sockeye and coho. The evidence is pretty strong that sea lice do develop around salmon farms, and those cause problems for pink salmon. Okay, and that's because pink salmon go to the ocean. It's these tiny little fry. They're very susceptible to these infections. But the evidence for viral diseases and all the rest, I'm not saying that these things don't occur. I would just say that the scientific evidence to suggest that the diseases associated with salmon farms are causing declines, the evidence is very weak and circumstantial at best. Okay, it doesn't mean it's not happening. It's just, if you want to ask what's the science tell you, it's very circumstantial. So again, it's one of these questions where, do we buy out and say salmon farms are the problem? Or do we say, you know what, we really don't know. We better, first of all, do some monitoring. That's one thing I didn't mention here. But to implement this sort of strategy that I'm advocating here means we have to monitor these things. We've got to monitor these resources that we're dependent on, whether it's water or trees or fish. No one wants to support monitoring these days. It's not sexy science. But when the rubber hits the road in terms of management, what they want to know is how many fish or how many trees are out there. And the only way to know that is by actively monitoring and doing a good job at it. Doesn't necessarily mean it's great science, but I believe it's the foundation upon which you build good management, is good monitoring of the resource that you're exploiting. In the case of salmon farms, the media has made a frenzy out of salmon farm issues with wild BC stocks. The evidence is pretty weak, except for pink salmon in some places where there's a salmon farm right in their migratory path.
Okay.
In the case of Fraser River, I'd say the evidence is almost zero. Others would disagree. Yeah.
So you said that setting up more hatcheries isn't necessarily an answer. What about developing artificial spawning grounds on the streams where there weren't any spawning grounds before?
So as you know, that's been a strategy in BC, and I think its success rate has been pretty patchy. In some places, it's clear that putting a spawning channel in does develop a bigger stock. Again, if you go to Bristol Bay and the Pebble Mine, for instance, the proponents of the mine were saying, well, we don't need streams, we can just put spawning channels in. And the questions that I posed back to them were, first of all, where's the water going to come from? Second, how are you going to maintain the disturbances that make that habitat viable? So you just can't cut a rain gutter in the earth and pour water through it. It needs to move around and erode, recruit gravel to the system. So a spawning channel is really hard to envision how that's going to work without a lot of intensive management to keep the system evolving through time, which is really what the salmon populations need. I'm guessing it can be done, but I think it's going to be very expensive.
Another question is, earlier on you showed quite a number of diagrams showing the productivity of different streams, and there seemed to be a very obvious 3-year cycle in quite a few of them. What's the significance of that 3-year cycle?
Okay, so it's a 4-year cycle, much like the Fraser. Well, the significance is, first of all, is that only a few streams seem to be doing that. That across the watershed, there's very little synchronization across the watershed. Do we know what's causing it? We still don't know what's causing it. Even in the Fraser, I mean, Ricker Point, or marking the Ricker Point of the South, decades ago. And DFO has spent tens of millions of dollars trying to figure out what causes this cyclic dominance in the Fraser River. We still don't know. So it's got to be, to have a cycle like that, there's got to be feedbacks in the system that we can't appreciate. Whether it's density competition among the juveniles or density dependence on the spawning grounds. We don't know. Yep.
Do you think that below the 48th parallel, a wall like this can be applied, or do you think that the habitats have, been destroyed to a point where they can't be recreated, and that we're so dependent on, hatcheries, and they've become such a, an industry? Do you think that it's viable for them to, put this back, or do you think they don't want to? Or?
I think that's a great question, because I think the results are applicable, and I think the results are applicable to questions, for instance, about restoration. If you think about stream restoration, typically, a bunch of people care about a certain stream, they get the money together, they get the political influence, and they go and they restore an individual stream. I guess my feeling is that that's going to be very limited in terms of sustaining fisheries and wildlife, unless you can do it at a broader spatial scale. So that would change your mode of operation, where you need to think more about how do you coordinate this across the watersheds. In the Columbia River right now, lots of dams are coming out. Not the big dams are coming out, but a lot of the small tributary dams are getting pulled out because they're just not generating enough revenue to make it worthwhile to read, or enough water to relicense them. And some people will say, leave them in there, they're not doing anything. And my feeling is if you start adding back little pieces of habitat to the system, you start developing the portfolio back, you may actually get some natural functioning back in the system. But it's going to be really expensive, because the system, it's really easy to degrade the system by putting roads in and preventing streams from meandering and things like that. But I think we can start using it in terms of restoration. But you're right, you go to a place like the Sacramento River, people forget, but the Sacramento was one of the biggest Chinook salmon runs in the world until about 100 years ago, when we put dams in and things like that. All our hatchery production is out of all our fish production is out of hatcheries now, and not surprisingly, they have a commercial fishery on it about once every 5 years. And in that 1 year, there's more fish caught than they know what to do with, so it's not a very productive fishery either. So you're right. Down in lower 48, we're not a lot left to work with, but we need. Restoration is hopeful, I think, but we've got to think about it in a broad spatial scale.
Any other questions?
Governments, you talk about what they want to do, or what they like to do, or what they have no money, it seems, or enforcement and all of that kind of thing. What do you see on both sides of our lovely BC? Because, in agriculture, our budget is so small in agriculture. And, you hear these stories, and I'm not a big fan of government, because I don't think depends on which government, and all of that. But
well, there's many ways to cut at that question. I'll start with just perspective as a scientist, as part of the scientific community. And this is where I think the prescriptive approach gets us in trouble. because government of Canada or government of BC says, all right, we're going to give you 1/10 of what your budget is really going to be. You tell us what you want to spend it on. And if you ask your typical fishery scientist, they'll tell you, I got some fancy new model or some new GIS that's going to produce the answers, and just give me a couple $1 million and I'll give you the answer. Well, we've been doing that for decades now, and we still don't understand what we're managing. Whereas the flip side is the scientists could say, well, we're going to use 3/4 of it and maintain our long-term records to keep track of how many fish are returning to our systems. Some would not call that science. I would call it science. Monitoring is part of science. So this is where I think scientists are setting ourselves up for failure by pretending that we can make these really provide prescriptive solutions. So that's sort of the scientific politics of things. Social politics, I don't know. I mean, that's, part of it is a lot of our conservation messages come from environmental groups that are focused around one species of interest. In a lot of ways, our environmental groups are special interest groups.
Yeah.
But in the case, again, up here at Pebble Mine, for instance, one of the reasons Pebble Mine is about to get shut down is because you have the natives, you got the sport fishermen, you got the commercial fishermen, and you got Greenpeace, all on the same side. And part of the reason here is they said, look, we have a working landscape here that it's not pristine, but it's damn close to it. And what we want to do is keep it as a working landscape. So I think in politics and how society engages in politics, whether you're in an environmental group or whether you're a fisherman, you got to think about ways to form bigger coalitions. And from that, you get more political influence. In a lot of cases, your goals, they may not be perfectly similar, but they will have parallels. But because we're special interest groups, we like to have our little Sierra Club or our little Fishermen's Association, and we actually survive because we pit ourselves against each other.
You said that hydrology and geochemistry had a chance to make some predictions about the challenges, or began at the ecosystem level, and then when you get to species, it's really connected. But I'm wondering, your example is salmon. Are there species out there for which this could have been easy and the prescriptions we could take with confidence, or is there something special about salmon that makes them really difficult?
I would say salmon are among the better species to predict, and one of the reasons is we can sample them really well. There's a famous fisheries biologist, can't remember who it is offhand, but he said fish are really easy to count. The problem is you can't see them and they move, right? So the problem is for a lot of aquatic species, we're sampling things that we can never really observe directly. In the case of salmon, we can enumerate these things better than any other fish species. Okay, how about terrestrial species? If you look at the hundreds of papers that have been published on, for instance, synchronized population dynamics in terrestrial species like the lynx hare and grouse and all these things, even at fine spatial scales, like on the order of tens of kilometers apart, they often show poor correlations with each other. What ecologists tend to emphasize is the significant correlations, because that's what gets you published. But those correlations are often, 0.3, 0.4. There's a lot of slop left in the data. So these same sort of ideas play out in a whole bunch of different species now, as people start looking at slightly different lenses.
Yeah. I was kind of thinking about, I've heard some people refer to sockeye and pink salmon particularly as the weedy salmon.
Yeah.
And it made me think of, how do people conserve weeds? Some weeds are certainly endangered somewhere. And
yeah, it's all about perspective for sure, but how do you conserve weeds? You distort the landscape. Right? And that's what we're doing, the exact opposite in the salmon landscape. We're taking the disturbances away. Again, whether it's like old growth or climax type species, again, the way you probably conserve it across space is by making sure there's heterogeneity in the landscape conditions. So yeah, I'm talking about salmon here. I mean, maybe I'm on the wrong planet here, but I really think the principles apply to just about any species you think of. We just haven't tended to emphasize that. So we're always seeking generality in our ecology, and we never turn it around and ask, well, is there local expression of the generalities? It's the local expression that ultimately matters.
So if you were going to come up with a property of a species in a place different from Alaska to test that, your approach on where next would that be?
Well, it turns out the plant literature is full of this stuff, and the evolutionary literature, one of the evolutionary literature is full of this in terms of the literature on bed hedging. So bed hedging is a big part of evolutionary theory, and it turns out a lot of different organisms do bed hedging, and what they're doing is spreading the risk of their progeny to different environmental conditions. Most plants have, or a lot of plants have seed banks. A lot of zooplankton and phytoplankton have sediment banks. Those are just ways that they're distributing the risk. So I don't think it's sound specific.
Any other questions?
I've got another one on because there's a lot of talk in BC on LNG and the various other mines. You touched on one example of mines, and obviously there's lots of roads that they're talking about, and power lines, and I don't know, whatever kinds of lines, and issues with caribou and moose, and on and on and on. So, I mean, all of these things are tied in.
Yeah.
Everything is tied. We're all tied together. We're all tied together. So, obviously that gets into politics. It gets into all kinds of different kinds of things. But what should we be learning about and going towards as far as trying to protect what we have in North America?
Well, I think that's a tough question. I think part of
And
the
then
answer.
run of the rivers, I also forgot to mention that because
Okay.
I thought about it, because that's another one that ties in very importantly to the system, river systems and
Yeah.
streams and all of that.
So part of the answer, I think, is that bigger is probably almost always better, okay, in terms of the planning and the protection. But at the same time, the heterogeneity, the variation across that landscape really matters. And it's often the case that you see arguments like, oh, there's sort of mining going to go in here, and it's just going to impact this little tiny piece of habitat.
Right.
Well, the reality is that little tiny piece of habitat, on average, may not contribute much, but under certain conditions, it could be the hotspot. So I think it's easy to write off little pieces of habitat just because, on average, they don't contribute much. So I'm starting to sound like a broken record here, but I think that heterogeneity across the landscape is something that has to be part of the goal for conservation and restoration. And it's Jack Stanford has this interesting metaphor. He calls it the shifting habitat mosaic. And there's two important words there. One is that habitat is a mosaic, but second, the mosaic is continuously changing across space and time. And that's where the processes come in, whether they're wildfire, whether they're geomorphic evolution, erosion from floods. Those are the processes we need to maintain. And you start putting roads and culverts in on rivers, you prevent them from evolving across the landscape the way they should.